All right, thank you for inviting me here. So my name is Andersson. I'm a research scientist at the American Museum of Natural History, where I work in the numerical astrophysics group. So we run numerical experiments of different processes. And today I want to talk to you about a numerical experiment that I ran some time ago, where I investigated the star cluster mass function in a few different simulations of a dwarf galaxy. And to kind of spoil the results a bit, basically I ran a few different models where I included different types of feedback sources. I ran one simulation without any feedback, for example, and then I had one with supernova explosions, and I have one as well with stellar winds and also radiation. And I investigated the star cluster mass function in these simulations. So if you're unfamiliar with this, I'm showing you an example here. This is a figure from Simon Porteous-Svart, Steven Macmillan, and Mark Giles in their review from 2010. This is the logarithm of the mass of a star cluster, and this is just a distribution function multiplied by some constant to kind of split them up. And there's quite a lot of empirical data on this mass function. Here are some different examples from different galaxies and different types of galaxies that we have around. And in general, you basically get a mass function that has basically a power law look to it. The slope here is roughly -2. So this is something that we can use as a constraint on numerical models. It's also very important. The shape of this mass function is very important for how feedback proceeds in galaxies. So if you're interested in understanding how stars inject energy, this is something you need to be concerned about. There's also quite a lot of debate in the literature. In this example, they included these lines to guide the eye, these dotted and dashed lines, to kind of highlight that there might be a truncation at the upper mass end. But this is something that is very much debated in the literature. And if I remove these lines, it's actually very hard to say whether there should be a truncation here or not. There's also some uncertainty of what this mass function looks like as a function of environment. So this is now assuming that it's a power law, and just taking the slope of that power law. So here's the -2 that I said before. But this actually seems to vary a bit in different environments, here shown as the star formation rate surface density. So there's some open questions about this mass function. So what I did was to run a numerical experiment where I simulated a bunch of dwarf galaxies. I actually simulated the same dwarf galaxy over and over again. This is set up to be very similar to the VLM galaxy. Has a stellar mass of 10 to the 7 when I start the simulation, fairly low metallicity. And in this simulation, I had a resolution of roughly 4 parsec, if you're interested in the details. The thing that I varied in this simulation is how I injected feedback. So I have one simulation where I inject type 2 supernova, and for this I basically assume that stars between 8 and 30 solar masses release 10 to the 51 ergs at the end of the main sequence. And if they're more massive than 30 solar masses, I basically assume they directly collapse into a black hole. This is a detail that I'll come back to a little bit later. I also have stellar winds, and these are fast winds for massive stars, so OB-type stars, and slow winds for stars that are on the asymptotic giant branch. And then I also included a radiation model. If you're interested in the numerical details, this is an M1 closure relation. I don't have time to go into detail, but basically we cover these different spectral bands here. And also another important thing that is the same for all the simulation is how star formation proceeds, and I just assume this Schmidt-like recipe. So this is now showing the stellar surface density of these galaxies. Here's the one with no feedback, and here's one where I only include supernova. I have supernova plus winds and supernova plus radiation. And then I also have this simulation where I have all the bells and whistles. So supernova, winds, and radiation. And one of the things that stood out when I looked at this is the fact that they have very different distributions of star clusters. And these star clusters actually show different mass functions. So without further ado, here is the mass function from these simulations. Again, the logarithm of the star cluster mass, and this is just the distribution. And we can start by just looking at this black line here. This is the simulation without any feedback. What you get is a plateau here, and then it kind of turns off into what I would argue is a power law at the upper end. And as I introduce more and more feedback, basically you truncate this plateau, you push it down further and further, and in the end, when you have all the feedback sources, you basically recover this power law distribution. I should point out that this distribution has a fairly steep slope. It's almost a minus 3 slope. And basically, if I were to go back to this figure that I showed in the beginning with star formation rate surface density, we are on the lower end. So it's getting minus 3 is a bit steep, but it's still roughly within that space. And I think some notable features here. First of all, just introducing stellar winds has a notable effect if we compare supernova plus winds to only supernova. Even though these winds are typically assumed to be have a very small effect, they do seem to affect this mass function quite a bit. And I think that's something that's quite interesting. So why is this? Why do we get different mass functions for this different feedback process? To do that, I made a very, very simple experiment. I basically took the simulations without any feedback, and then I artificially introduced limitations to growth, which is basically what feedback is. When you get feedback, you inject energy into the gas, and it's very hard to form stars. So you're limiting the mass growth of the galaxy. And the same way I did this in the no feedback case by just selecting stars below some mass or some age limit. So going from 50 million years, we have this, and then 25. This is the one that I showed before. 25 is what I used for all the other simulations. And we have 10, 5, and 2. And basically what I seem to recover is roughly the mass functions that we get for the different feedback channels when the timing corresponds to roughly what the timing is for the type of feedback source I include. For example, type 2 supernova occur between 5 and 10 million years, and in this case, that's roughly what I got for the feedback simulation. Whereas when I introduce all the radiation and the winds, which start immediately after star formation, you will recover something that's more similar to that. So that's something that's quite interesting. I also mentioned that I have this assumption of directly collapsing stars to black holes when they are more massive than 30 solar masses. This is an assumption that has quite a lot of uncertainty. So I went ahead and tested what would happen if I just alleviated this assumption and let all stars up to 100 solar masses inject energy when they leave the main sequence. And this has a similar effect to having an earlier onset of feedback. And that kind of makes sense because a star of 100 solar masses has a much more shorter time on the main sequence. So basically this also becomes a lever that I can pull to change the injection timescale for my feedback. And this is something that is quite interesting and something that people should probably be taking into account when they make these sorts of assumptions for these models. So that's kind of what I have to tell you. That's the story of my talk. I think the cluster mass function can be used as a constraint for galaxy formation models. I found that feedback changed the cluster mass function. Basically, the main conclusion is that pre-supernova feedback prevents cluster growth, and that makes the mass function into this fairly steep power law. And at the end, I also mentioned the details of how we implement these types of models in our simulation actually matters for the results that we get out. If you're interested in any of the details, this is in a published paper that I published earlier this year, and I'm very happy to take any questions.
Or is it easier, are you particularly favouring
I mean, the honest answer is that I ran these simulations because I had the initial conditions and I wanted to test the feedback models, and they turned out to be interesting. But I would like to do this follow-up in a more massive galaxy, especially like Milky Way mass. And this is these models are not super expensive to run, so I could probably get away with running at the resolution I have. It's manageable.
Thank you. Any other questions?
Yeah. I think it was the second slide you showed with the data on the mass function for different galaxies. Yes. So let's go to the AMNH galaxy. Like that goes the log n goes to 6.5 or thereabout, and it's a fairly flat slope. So would something like that be explained by your model, or the fact that there is merging involved with some positive feedback and change things?
So I should start by pointing out that like this is reality, right? And my model, the only one that probably should be compared to reality, is the one where I have all the numerical models. Like we know that stars, they do go supernova, they do inject winds, and they do have radiation. So if we want to compare with reality, we should probably take the one where we have the most realistic feedback model. So that's more like, I think the way I want to sell the result that I found is that this is kind of a numerical experiment, what happens when we have different models. But I think the antennae, like it's a very special galaxy, right? It's a huge major merger, super messy system, something that's probably more akin to an early universe environment, where we have more gas and more big mergers happening. I would be very interested in understanding this, why you get this mass function, because this might be able to tell us something about, for example, how globular clusters form in the earlier universe, or how young massive clusters form and how they compare to globular cluster progenitors. Yeah, I don't know if that answers your question, but that's kind of how I think about it.
Okay, do you have any other questions? Yes, sir.
Nice. So it is found that at high redshift, galaxies are having, more concave features and also maybe higher surface density. So would you say that is possibly that in the early universe, the galaxies having less feedback as in your simulation?
I think feedback is probably similar unless you go to very, very high redshift, like if you get stars that have basically zero metallicity. Otherwise, I think that feedback processes are probably similar, but the environment is very, very different. You have a lot more gas around at high redshift, so your dynamical instabilities are going to be very different. Galaxies don't tend to be nice, flocculent, spiral galaxies either at a very high redshift. So I think that's more important factor for high redshift.
We can take one more question if there is one. No, let's thank our speaker again. Thank you. Rotating small scale magnetic fields at the surface of pendulum.
Okay, good evening.
You're on.
Well, thank you for being here. I'm happy to talk about my work. People who know me know that I like to talk about two things in life: magnetic fields and M dwarfs. So, no surprise here, I'm going to talk about magnetic fields and M dwarfs. And I know a lot of people are interested in exoplanets. So let's take the exoplanet route to introduce this for a minute. Imagine you have a planet orbiting a star. You hopefully have a signal that is just perfect, and from this radial velocity signal, you can deduce the mass or radius of the planet. And you can tell a lot of things about the planet, and you can try to see if it's habitable. Now, the The thing is, M dwarfs are very interesting because they are extremely numerous around us. Most of the stars are M dwarfs. And if you have an Earth-like planet, because of the smaller mass and radius of the star, you're actually going to induce very big signals. The thing is, if you start studying planets and you wonder whether it's habitable, you can't stop at this. You also have to consider the fact that stars are actually much more complex than they look like. I am trying to become that person that puts this drawing in every single presentation, just because I like this drawing a lot. And this is now what I picture when I imagine a star. I forgot to put the mic on. Is this fine or? Oh, okay, perfect. Working, okay, that'd be better. So the thing is, if you look at a star that has magnetic fields, it's going to have activity, stellar winds, things that can actually impact the habitability of the planet. So it is very interesting to characterize the magnetic field of the star. So now let's talk about the magnetic field of the star itself. How can we measure it and characterize it? One way of doing it is, there are two main techniques. One of them is to use spectropolarimetry. So from polarized light, you can actually try to deduce the large-scale field structure at the surface of the star using the fact that the Weizmann effect is polarized. So if you have a magnetic field vector, depending on where you look at, you can see either circularly polarized light or linearly polarized light. And if you have a star that rotates and has huge, large-scale field structures at the surface, you can actually invert the problem, and from the variation of the signal that you're going to get, reproduce the large-scale structures. This is typically what's done with Zeeman Doppler imaging, ZDI, that is very powerful at doing this. Another technique is to directly model the spectrum of a magnetic star, putting all the physics you know about the star, the atmosphere, and so on, and including the Weizmann effect. And that means you can have, for example, a transition like sodium, like this one here, that has a given shape for a non-magnetic star, and under the influence of the magnetic field, you're going to get a splitting of the spectral line. And this is very powerful too, because it turns out that you have some lines that are very sensitive to the magnetic field and some that are not very sensitive to magnetic fields. So you can actually have a very good constraint of the magnetic field strength of the star. One of the things that I find interesting is that these two techniques seem to probe similarly different things. Because from the large-scale field structures, from ZDI, you get large-scale field structures, but you get much less strength, overall magnetic field strength, than with direct modeling. So I really like this picture from a very good review by Kochukov in 2021 that shows what would happen, what you would expect if you had a full, huge dipolar field at the surface of the field, for example, where you can see a polarized signal in red and the unpolarized spectrum in blue. And what would happen if this same structure did not occupy the entire surface of the star, for example? So you have a filling factor, doesn't fill the full surface. Or if you have some randomness in the magnetic field at the surface of the star. And you can see that the unpolarized light actually changes significantly in this case, while you would have a similar polarized signature. And this tells us that maybe we probe different things. So is there a link between the large scale and these small scale fields? What is this link? Those are the things that we want to address, and to do that, we need measurements. So to do this, I've developed a code called ZTurbo that is based on Turbo Spectrum, that is a spectral synthesis code that is very powerful for low mass stars, and the Weizmann codes that was not really designed for cool stars. And so with this, we can model the spectrum of low mass magnetic stars. Since then, we've applied this to multiple data sets. I just wanted to highlight with this slide the work that's been done with Julie Sage during her REU project here this summer, where we've applied it to wine red data that was recorded. So wine red is a high resolution spectrometer that is installed at the Magellan Clay telescope. It has a fairly short wavelength range, but it has a very high resolution and can get a very high signal to noise ratio in a very short exposure, which is great. So you have an example here for this star where you can see in black the spectrum of the star, and you have in purple dashed the line that represents the model with no magnetic field, and the red line is the model with magnetic field. And again, because we have some lines that are not sensitive to magnetic fields, and some lines that are very sensitive to magnetic fields, we actually can see the intensification effects and quantify the magnetic field strength at the surface of these stars. I've also applied this to other data sets. We've applied this to SPIR data, for example. SPIR is a high-resolution spectropolarimeter that is installed at the Kennedy French Howard Telescope. And it's great because it allows us to actually get both the polarized signal and the unpolarized signal. It has a large wavelength range. It was designed to also detect planets, and a high resolution. So here you have an example for 6 stars, where black, again, is the spectrum of the stars. And you can see that the shape changes for very magnetic stars. And in green, the non-magnetic model can simply not reproduce this line shape, while the blue models that include magnetic fields can. And what's great also is that with SPIR came the SPIR Legacy Survey. That is a large program that was allocated more than 300 nights from 2019 to 2022. So we had a lot of stars that we observed. So we can actually measure the magnetic fields for a bunch of these stars and put them, for example, in a magnetic field Rossby number diagram. Now the Rossby number is this ratio between the rotation of the star and the convective turnover time. So the idea is if you increase the Rossby number, you increase rotation periods. And empirically, people had noticed that activity scales with rotation in stars. And in particular, it produces this saturated dynamo regime, where you can see that you have sort of a constant magnetic field independently from the Rossby number. And at some point, you do have a relation between the magnetic field, the activity, and the Rossby number. Well, we see the same thing with the magnetic field. This is something that was observed by Reiners et al. In 2022, before, and we're able to actually reproduce the same relation. Now, the thing that is interesting is we have partially convective and fully convective stars in this sample. And fully convective stars do not have the Ygal Klein, which means the very classical dynamo models, sun-like dynamo models that relies on the Ygal Klein, need to be a little revisited for those fully convective stars. And what I found interesting in our samples, we actually have a few partially convective stars that have very low magnetic fields, but we have very good fit to the spectra. That means I really don't need to include magnetic fields in order to reproduce their spectra. So it could mean that we indeed have really a spread in the data points here, and that we do have some stars that have similar Rossby numbers, if we have the rotation correct, and yet don't have a very strong magnetic field. So that's one result. Another result I wanted to highlight, and that is kind of cool, I think, but I'm working on right now, is that because we've observed a lot of these stars for periods of time from months to years, we can actually measure the magnetic fields at different nights. And we end up with data points that are pretty much magnetic field as a function of time. And so we get a time series of measurements. And from this, we can fit a Gaussian, quasi-periodic Gaussian process, which is something that's been used before actually on large-scale field, on longitudinal field, for example, in order to measure the rotation period of the star. And interestingly enough, well, that was expected, but we retrieve the rotation period of these stars. But now we can actually use that to also see how the small-scale magnetic field evolves with time. And we see, for example, that for EVLAC here, we do have an increase in the amplitude of the signal at a certain epoch in about 2021, if I remember correctly. And this can tell us that we have a change of the overall inhomogeneities at the surface of the star that would cause the variation in the magnetic field we measure with phase. And interestingly enough, we can actually go into much more details and look at what is the distribution of the fitting factors at different nights. Now, the fitting factors is something that I did not introduce before on purpose to go faster. It represents sort of how much of the star, of the surface of the star, is covered by a magnetic field at a given strength. So here we've modeled actually these stars by considering that we have 0, 2, 4, 6, 8, or 10 kilogauss fields that cover different parts of the surface. And we can see that if we take this data point here, when we have a magnetic field of about 4 kilogauss, we have a certain distribution. But if we look later during the phase, we have another distribution. So I was perfect. I can finish with this. Other thing, we've noticed that for some other stars, the field decreases completely over time, over the course of several years. So that also is interesting. And I will just leave you with my bullet points here and take any questions if you have some.
Thank you very much. I would expect there to be a very strong degeneracy between the fraction of the stars magnetically active and magnetic field. Is that not the case?
So in some cases, yes. Actually, interestingly enough, it's much more the case if you have a star that is seen pole on, for example. However, the approach that we've used here is we have a huge degeneracy usually between components that are very close to one another. This is the reason I have steps of 2 kilogauss. If I take steps of 1 kilogauss, for the stars we observed, we've noticed that it just increases computation time, and we have a huge correlation between the 1 and 0 or 1 and 2 components. So we just said, okay, we're going to sample broadly.
Also, do you know if these stars are uniformly rotating, or because the sun is not uniformly rotating?
No, so you may have differential rotation in some of these stars, and well, this for now the assumption is just a solid body, right? It's obviously the Gaussian process is trying to capture some of the fluctuation in the magnetic field over time and so on. Gaussian processes are kind of a dark magic, right? Some papers have shown that it actually corresponds to things that can be linked to physical properties, especially by looking at the sun. But here we just wanted to see whether we were capable of retrieving the rotation period of the star, and whether we see some things that are actually consistent with the change in activity at the surface of the star.
So you have a lot of interesting data with the spiro. You can do the large scale and the small scale at the same time. Do you see any correlations between large and small scale?
I think this is definitely something that I forgot to mention at the end that I wanted to mention. No, and this is also what's interesting, is that if we look at the longitudinal field, these huge variations that I see, for example, here, I don't see it. When I see these changes in amplitude, for EV-lag, we actually see the same thing in the large scale field. But for other stars, we don't see the same behavior at all, which tells us that either you have uncorrelated phenomena that lead to these fields, or that the relation between the two is highly complex and not at all straightforward.
Thank you. Any other questions?
Does your model have to assume a dipole field or a higher model?
No, so we actually cheat a lot, and we assume a monopole. So that causes any problem to Maxwell, right? But no, we assume that the field is radial in the point of the photosphere, which for the small scale is actually not that big of a problem usually. We've done some tests, like taking a dipole, trying to measure the magnetic field we get with our linear combination of monopoles, and we get some things that are actually very consistent. We do have some small offsets from time to time, but the trends remain the same.
I admire your honesty. Ever since graduate school, I've been astonished at how poorly magnetic models of stars has the boundary conditions at infinity.
Sorry?
That's like boundary condition at infinity. It's just ignored.
Yeah, we usually
Great. Any other question?
I have a quick one. Do you have optical monitoring of this? Can you see the variations in flux in the overall brightness of the star?
This is actually a good question that I'm currently trying to explore. I'm not sure we have it for all of these stars very precisely. You have some work from Artigo that just published a paper, for example, that was looking at what claims to be a variation of temperature. So you could also have other things that lead to variation, right? What's great with this method is because we have non-magnetic and magnetic lines, we actually have a little more confidence that what we're seeing is magnetic fields and not something else. But for photometry, it would be interesting to have.
But yeah, and you should get simultaneous monitoring while TESS is looking at those stars. That would be exquisite.
Yes, that would be great. The thing is, this is a large program that, I mean, on the course of several years, right? When this started, I started my PhD. I didn't have much of a say on the matter.
Anyone else? Let's thank our speaker again. So our next speaker is Fengwu Sun, CFA. Most of cosmic star formation at radiation time is still a zero project.
Okay. So I will start to talk about something further away, which is the cosmic star formation density at redshift 5. So I'm Fengwu. I'm a postdoc working with Daniel's group on JWST high redshift project. So I'm going to show something that I started working on when I was still a graduate student at the University of Arizona. The star formation, The easiest way to detect the new star is forming is in the UV band, right? Because like young massive stars, they are bright in the UV. But sometimes you get a dust, which can be quite annoying, that obscure the UV light. So you have to go to the infrared band to see the reprocess the UV light. They become the thermal emission in the infrared. And you can do this kind of measurement of how many star formation is there in a certain volume from redshift 0 to very high redshift. And you have this kind of plot called as a Lilly-Maddow plot. Y-axis is the star formation, the volume density. X-axis is the redshift. So below redshift 2, the measurement is relatively easy. It has been done with a lot of telescope. But beyond redshift 3, it's become difficult to take spectra of galaxies from the ground. And that's really where we need the most advanced facilities in the extragalactic field. For example, ALMA and JWT to really measure things. To measure the obscure star formation density, the typical method is you need to get the luminosity function. You, for example, detect the galaxy that is in dust continuum with ALMA, and then you look at the overall the spectral energy distribution and get a photo Z, or you have access to some radio interferometer, and you can get the CO line scan of these kind of galaxies, and then you count how many galaxies are there, and plot out the luminosity functions, and you integrate the luminosity function. You get star formation density. It sounds very easy, but actually it's not, because if you look at the redshift distribution of these dust obscure star forming galaxies, most of them are at the redshift 2 or 3. And if you want to find something really at high redshift, let's say beyond redshift 4, it's like finding a needle in a haystack. And some of these galaxies are very dust obscure. For example, this is one of the first dust star forming galaxies people have ever detected beyond the local volume. So this is the HDM 850.1. At that time, people detected it and look at the deepest HSD data, taken forever, and there's nothing. And until last year with JWT NearCam, we started to detect the stellar continuum of this galaxy and really measure how many stars are there. And you can get access to ALMA and try to get a CO scan of these kind of galaxies. And for these quite luminous galaxy, you need 8 hours on-source time to get a redshift confirmation of these galaxies. And let's say if you go 10 times fainter, you want to get the 10 galaxies like this brightness and do a statistically meaningful sample. What will be the time request for a big telescope like ALMA. So ALMA in each cycle, they spend 100 hours of time at least to do in this business to measure how many obscure cosmic star formation rate is there at around redshift 5. And over 3 years, there is a factor of 30 discrepancy at this regime. So I decided to look at this on my own, try to make things more accurate. So we start to use this set called the spectroscopic survey of bias halo in the reionization era. It's actually looking into quasar, not really does these star forming galaxies. So we select 25 quasars at redshift 6.5 to redshift 6.8, try to understand whether these most massive black holes reside in the most massive dark matter halos at this early regime. So the thing that we use is called NearCam Grism. When I was a graduate student, I commissioned a calibrated instrument. So you can take the spectra of everything that we see in the field of view, and including the quasar. You get the spectra like this, O3 H beta. And for all the companion galaxies at the same redshift, you also get the O3 H beta at the same time. So you can immediately know that quasar indeed reside in galaxy over densities traced by these O3 emitters. And we have another ALMA large program, 100 hours, looking at the same quasar fields, but using the carbon-2 lines in the far infrared as a tracer. So we get ALMA continuum image. Lots of the dots here are dusty star forming galaxy from redshift 0 to redshift 7. Most of them are not at the quasar redshift, so I'm particularly interested in looking for the JWT spectrum of these dusty star forming galaxy at redshift 4 to redshift 6 that fall in the field of view, and we have the spectroscopic access. So these are 5 examples of the spectra that we get. I'm showing the 2D image, JWT images here, and also 2D spectrum, 1D spectrum. You see a lot of them have H alpha, nitrogen 2, sometimes sulfur 2, and this one is even at higher redshift that we have access to the H beta O3 doublets. So we are doing the Grism spectroscopy at 3 to 4 micron, and we can confirm this high redshift dusty star forming galaxy at redshift 4 to redshift 6 through the H alpha O3 complex. And the image of this galaxy look like this. I'm showing the HSD image, JWT image on the left, and the ALMA image on the right. That's the dust continuum. See, lots of them are dust reddened with complex morphology, sometimes merger, and the first one is actually gravitational length. So we start to count how many galaxies there. Okay, the y-axis is the number count. X-axis is the brightness in the millimeter band. So all galaxies at all redshifts should follow these solid black lines, and different large programs given different results. I show this color bands. We are observing 25 fields, so we average out the cosmic variance through these 25 fields. So we are most of the uncertainty that I show in this plot, all measurements, are post-noise. We don't have uncertainty from photometric redshift, which is a big concern for this literature sample. And we also average out the cosmic variance. So we immediately find that our measurement is almost 1x higher than all of the existing measurements based on the Hubble Ultra Deep Field. Because Hubble Ultra Deep Field is just so tiny, it's 2 times 2 square arc minute on the sky, and when you want to measure something really massive, you hit you may hit the void or hit the over density, right? So the cosmic variance is really important for this business. In this regard, there's no galaxy like that in the Hubble Ultra Deep Field at all. So this is another way to say it. It's infrared luminosity functions, and I'm showing some literature measurement and some simulations. It's actually interesting. Real observations are more sensitive to the bright end because you have better spectral sensitivities. And at the faint end, the simulation is better because you require less computing resource. You can do it with smaller box, right? And our measurement is here. That is the best fit infrared luminosity function that I get. Sort of agree with previous result, but all of us, our measurement has specs. And here is the stuff machinery density as a function of redshift. I'm showing in red, orange. These are obscure stuff machinery density. You see big, it's a mass at redshift 5. And some of the observations are above the thing that you measure from UV, which is shown in blue. Some of them are below. And our measurement is solely about the UV measurement at this redshift. That tells you, when you compare with the UV measurement, 2/3 of the cosmic stuff machinery density is obscured by dust. And the total stuff machinery measurement that we get, combined with the UV together, is almost 2 times of the classical model plot. So we can also plot the stuff machinery density, stuff machinery functions. X-axis stuff machinery, y-axis is number count. And you see how the UV traced population showing in the blue lines, what are their parameter space compared with what we observe with ALMA and JADES in the red line. These are obscure stuff machinery density. So basically, the two populations, the divergence happens at around a few tens of solar mass per year in stuff machinery. And if we integrate the stuff machinery functions at a given stuff machinery threshold, we will get a plot like this. So we can find out that the massive galaxy with stuff machinery larger than 10 solar mass per year contribute to most of the cosmic stuff machinery density at this redshift. Well, most of them are obscured in respiring UV, so you miss that with HSE survey. I put some remarks here. First of all, cosmic variance is really important for this business. If you go to a very narrow field, go very deep, it probably won't helpful because like H2DF, it clearly hit a void of a redshift about 4 dusty supplement galaxies. And secondly, the obscure stuff machinery density is probably higher than the classic model prescriptions, and it's still larger than UV at the redshift 5. But there are still lots of uncertainty. First of all, I need to convert the ALMA flux density measurement through some stuff through some fine infrared SED assumptions to IR luminosities. And do we really trust the SED, the spectral energy distribution, those can tabulate at redshift 5? There are a lot of uncertainty. Second thing is we are totally based on the redshift 0 calibration of IR luminosity to stuff machinery calibration. And whether that's still valid at redshift 5, is the initial mass function changing at the higher redshift? I'm not really sure. So clearly, we definitely need a better statistic, and I'm showing that the direction we are going to. So this is hours of near-cam Grism wide field slit spectroscopy observation over cycle 1, cycle 3, cycle 2, cycle 3. We are about to write cycle 4 proposals, and you'll see that the time used in this observing mode is increasing by 60% every cycle. So the thing happened to us is in cycle 3, we are very lucky that through my PI, co-PI, co-I program, we got 1,000 hours in cycle 4 using this mode, try to search for these kind of galaxies over much larger volume towards deeper depths. So I hope that we can deliver very good statistic maybe next year. And here are my takeaways. I'm happy to answer questions.
Congratulating you and another speaker. Finished within seconds. So all of this dust, is there a theoretical problem making as much dust as is needed by redshift?
Can you say that again?
Is there a theoretical problem making as much dust as you need to have all the substitution?
I think some of them, yes, there need some theoretical problem. Like you have to assume, combine all the dust production channel together, like supernovae and some fancy model even need like some dust directly produced by ISM after some shocking. I'm not really expert in the theory side, but indeed some of the galaxy, when you observe certain very large dust mass reservoirs, they indeed introduce challenge to theory. Just like when you see supermassive black holes, maybe if they are too massive, that introduce challenge to theory. That's the same.
Any other questions? Please go ahead. Yes, sorry, please. Yeah.
So for the objects that are lensed, is there any uncertainty that comes from the flux, the conversion from going from flux to luminosity with regards to the lens modeling?
I include lens modeling into that, and the lens magnification factor that I get is around 1.9 plus minus 0.3, and that is include the alpha is included in all my following analysis. So there is some uncertainty, but not a lot. The infrared luminosity function is almost flat. It's quite flat, so that's not introducing a lot of error.
Go ahead.
What's the source of the scatter of this redshift? Is it like cosmic variance or uncertainties?
You mean
in the Mandel plot? Yeah.
So I think most of the uncertainty is from photometric redshift. So you have to assume some kind of prior distribution of redshift of everything, and then try to get the posterior distributions. And these posterior distribution of redshift, they are huge. And some of the observations are more sensitive to certain amount of populations. They overcount, and some of them are undercounting. So there's a lot of difficulty there. But if you have spec these, you immediately know basically the wave function collapse, and you immediately know how many objects are really at this redshift regime, so you can do better statistics.
Thank you. Any other questions? So thank our speaker.
Hi, thank you for that. Let me get this plugged in. Okay, yes, my name is Justus. I'm here to talk to you about these ultra-red flattened objects. That was actually a great introduction for a lot of the stuff I want to talk about, because these are really heavily dust-obscured galaxies that we didn't necessarily expect to find with the first set of James Webb data. So these are a bunch of galaxies, as you can see. And what I want you to notice is the kind of different morphologies that you can see from galaxy to galaxy. So you have a typical kind of bulgeless spiral galaxy here. You have a spiral galaxy with more of a bar, more bulge-dominated spiral galaxy here, more of your elliptical type galaxy, and an irregular galaxy that's just kind of all over the place. And what these morphologies can tell us is kind of give us some hints about how these galaxies formed, what kind of processes have affected them. These are local galaxies, though. I'm going to be talking about more distant galaxies. So here's another Hubble image. And you can still kind of see some of the same general shapes, but just not as clearly resolved. So a brief refresher on galaxy morphology, because I'll be talking a lot about that today. So as I said, morphology shape kind of reflects assembly history and how these galaxies are growing and changing. There's a couple of basic ways to classify a galaxy's shape or morphology. One is the Sirsic index, which is a measure of the concentration of the light profile. Some more elliptical type galaxies have these more concentrated light profiles, and disk-like galaxies have these less concentrated n equals 1 disk-like light profiles. That's one way. Another easy way is just the axis ratio, where you take the ratio of the short axis to the long axis, and that gives you a general sense of the projected 2D shape, which you can make some connections to the intrinsic 3D shape from that. Okay, so moving into the James Webb data, here's some Hubble data of the S-Max cluster. And then you can see as we go to James Webb, there's a whole lot more detail. You see new types of galaxies pop out that we didn't see before. So just kind of Hubble on the left, James Webb here. What I think is really interesting is, there's obviously all this detail popping out, but also there's all these new types of galaxies that weren't seen with Hubble. These really striking red objects that you can see all throughout here. Basically what that means is in Hubble, which is measuring optical rest frame wavelengths, these galaxies were invisible to Hubble, but James Webb can easily resolve them. And it's kind of the first time we've been able to resolve the morphologies of these really dust-obscured galaxies. So yeah, it's a whole new window. We're tracing the rest frame near infrared, so we can actually study the morphology of these galaxies in the type of light where most of the stellar mass is being traced. I already set this up nicely. Optically faint galaxies are important because they contribute a lot to the star formation rate density throughout time, and possibly going even farther than this plot shows. So what do we actually expect them to look like? Since we weren't really able to resolve them before, the expectation was basically that these have to be kind of compact, small galaxies, and that's the only way you could drive a large enough dust column to make them optically faint. So a quick cartoon illustration of that, you have your galaxy in your observer. It's a fairly large spiral galaxy. You have some dust in front of it. Not enough dust to completely obscure it, so we can measure optical light and figure out its morphology that way. But if you have a smaller, more elliptical type galaxy with dust in front of it, most of that optical UV light is going to get attenuated and then re-emitted in the infrared. So this is kind of the general picture people had before James Webb turned on. So what did we actually find? So as expected, we did find lots of these little red compact galaxies, like the little red dots that you hear about. But more unexpectedly, we also found a lot of these more elongated galaxies that are also extremely red all the way throughout the extent of their bodies. This is surprising for the reasons I said before. Because they're ultra-red and they're flat, these have been called UFOs by the people that discovered them. Okay, so what we did was we leveraged the survey area and depth of JADES, which was much better than any of the early release data. And we looked for these same types of objects in the JADES data, just imaging and spectroscopy in GITS north and GITS south. And we found way more, and really some really striking ones as well that are incredibly elongated, very red throughout. So basically the question we want to ask is, what are these things? What are their basic properties? What are their shapes? And what drives that optical faintness? Why are they so red throughout the entire extent? So as a first step, we just did some stellar population fits with the prospector, and basically found that these galaxies are generally located at redshifts between 2 and 4, sometimes a little farther out. You can just pay attention to the red squares and red circles in these plots. So they're generally also pretty massive as well. They're really forming a lot of stars. They're way above the stellar main sequence for their redshift, except for the highest mass ones. Those kind of dip off a little bit. And over here, I just want you to focus on the x-axis, which shows the dust attenuation. And compared to non-optically faint galaxies, these have large quantities of dust, which is what we think is driving this attenuation, this redness we see in them. So more about the morphologies. So if you have some kind of dust-driven optically faint galaxy, we might expect them to be compact and have these high Sirsic index profiles. But we actually see, regardless if we're looking in like F444 or F200, is that these galaxies tend to have very low Sirsic indices, which would be more indicative of being a disk-type galaxy. Turning to their axis ratios, for a compact galaxy, you would expect it to pretty much look like a circle anywhere you look, regardless of your viewing angle. But what we see is that there's a distinct lack of circular projected axis ratios, and they tend to be more skewed towards this like 0.4 range, which is interesting. So it's unclear from these two quantities alone whether they're disks or something else. So I'm going to talk a little bit about actually inferring the true 3D shapes from these 2D projections. The axis ratio is just reflecting, what the 3D shape looks like projected onto the sky. If you have different shaped galaxies and you view them from random angles, they're going to have their own unique axis ratio distribution. And so we can basically model this in a type of way to kind of come to stronger constraints about what fraction of types of galaxies might make up the observed distribution we see. So taking a step back, I'm going to go through a few examples. So different populations give different axis ratio distributions. So you have some kind of spheroidal cat or galaxy. It's going to have its unique axis ratio distribution. No matter how you look at it, it's going to be pretty circular, around an axis ratio of 1. Compared to the observed distribution, this is not what we see at all. If you have a disky cat, complete with spiral arm, then you expect something more like this. So if you look at the disc edge on, it's going to have a very low axis ratio. If you look at it face on, it's going to have more of a circular axis ratio. So you can kind of get the full range of axis ratios. And this does pretty good, but we're lacking these kind of higher axis ratio objects that we might expect. Third general type you can have is a prolate cat or galaxy. This is my cat, Mowgli. So he's elongated in one direction. So that has its own unique axis ratio distribution. And this actually does a pretty good job of matching the observed distribution, kind of just missing some of these lower axis ratio objects. So let's get into the modeling. We used a software called the Beast, developed by Sedona Price. So we can basically infer how much of each type of galaxy contributes to this observed distribution. And so in our first model, we let everything be fully free. Galaxies can be any kind of shape. We're viewing them from all types of angles. And so on the top in red is the model distribution compared to the observation. And you can basically, it spits out basically what fraction of each type of galaxy you expect. So in this case, for the fully free model, we basically have 90-ish% prolate and only a very small fraction of disk-like galaxies. In model 2, we assume that we're only viewing these systems more or less edge on. And so in that case, we still get a pretty good match to the data. But because we're kind of enforcing more of a disk-like interpretation, we end up with more of a disk contribution, but still a very strong prolate contribution. Final model, we're trying really hard to make these things disks. So we basically say that they have to be more or less oblate, which is another word to say disk. So in that case, disks kind of start to dominate the distribution, but we still have a fairly large fraction of prolate galaxies. So this is kind of telling us that at least in this framework, we're expecting a fairly large contribution of these galaxies being prolate, regardless of what we try to model them as. So that's kind of interesting, because these are really massive. In the low redshift universe, massive galaxies tend to be either disks or spheres, and it's the low mass galaxies that tend to be more prolate. Another issue is the dust attenuation. So for an edge-on disk, you can imagine that the column density is large enough to make it optically faint. But if you're looking at like a prolate galaxy this way, there's not a lot of column density to go through it, so that's kind of surprising. You might expect, if a prolate galaxy was going to be dust obscured, you'd be looking at it this way. So kind of what is driving this? Are they just intrinsically very dusty? Is there something wrong with our modeling? We're doing single Sirsic fits, maybe a double Sirsic fit, or something with the ellipsoidal approximation for the modeling is off. Interesting, and I'd love to hear any ideas that people might have. So yeah, thank you. That's all I have to say. Thank you.
Thank you. Could you go back one slide, please? So that object doesn't even look prolate to me. It's like clearly fatter on the left and on the right.
Yes. So I think there's some interesting, maybe not all of these are prolate. I mean, I think we have to have a contribution from thin disks, but this is kind of just a weird one anyways because of how that shape is.
Questions to the audience?
Yeah, sorry for missing, but I was wondering if there's a selection effect that disks will be more likely to be selected edge on, right?
Yeah.
And then you can when you see the face on, you miss the outer parts.
Mm-hmm.
Yeah. Did you try including this?
So in the second model, we basically say that we're only looking at systems edge on.
Yeah, but then some of the disks that seem like face on would be seen as spheroid also.
Yeah. So that might be something we should consider modeling in the future, because in our whole sample we have some of these circular ones, but we kind of threw them out. Basically, we wanted to only select the elongated ones instead of those.
So for these UFOs, what is the dominant source of the emissions you see from JADES? The star or the dust?
Sorry, can you say that again?
So the emissions you see, which is flat, distributed across the galaxy, is from the stars or from the dust?
We think the redness is coming from dust. You seem to have dust
Basically, what you are talking here is about the distribution of the dust rather than the stellar.
Yeah.
What is stellar masses of the things?
10 to the 10-ish, up a little higher, and some a little lower.
Okay, so.
But yeah, roughly around 10 to the 10 is probably the average.
Okay, so you'd expect disks.
Yeah, exactly. Yeah, we tried really hard to make them disks, because that's what everyone thought.
There's another question, maybe they are first. I want to representatives, thank you very much, and thank all of our speakers. I mean, you're